Higher Physics Notes, Unit 1, Section 2 Forces. This is part 5. We're still considering Newton's second law, and we're just going to have a brief look at rocket motion, something you did at National 5, a reminder of friction, and then pretty much reminder of terminal velocity. So nothing drastically new in this section. So first of all, rocket motion. So just a couple of points to bear in mind. So the scenario here is that a rocket is ascending, and you should always remember that when a rocket is involved, there are two bodies to consider. There's the rocket itself, but there's also the exhaust gases. And the exhaust gases are a massive body, just as the rocket itself is a fairly massive body. And as I'm sure you know from National 5, there's an action force. It's the force of the rocket on the gases as the gases get pushed out the back, and there's a reaction to that. Newton's third law reaction. These are both forces, of course. Whenever you mention the word action and reaction, always put in the word force, to be clear. And that reaction force is the exact opposite of the action. So if the action is force of rocket on gases, this is the force of the gases back on the rocket. Now notice only one of these forces is acting on the rocket. The force that's acting on the rocket is the reaction force up here, this one, and that is commonly known as thrust. And it's the thrust that makes the rocket move. Okay, so there's the Newton 3 diagram. If we go back now to a free body diagram for the rocket, free body diagram for a rocket. Well, we now know that the forces are thrust, up the way, and of course not forgetting the weight of the rocket down the way. Now basically those are the two forces. We generally neglect air resistance when it comes to rocket situations. And when we apply Newton's second law here, we get ma. So if we assume the rocket is accelerating up the way, then the unbalanced force is given by the thrust minus the weight mg. Okay, and that of course equals ma. Now, generally speaking, so there's our equation. Generally speaking, the thrust remains constant throughout the burning of the fuel. So it doesn't matter whether the tank's half empty or quarter empty or whatever, the thrust remains constant. The mass is going to change, so we'll come to that in a second. G, of course, is always constant. And the acceleration will depend, therefore, on the difference between these two forces. Now the one that we're interested in now then is the mass m of the rocket, because it is going to change during the motion because fuel is used up. So the key point I'm trying to make here then is that as the rocket ascends, fuel is used up. That causes mass of rocket decrease, which means weight of rocket mg decreases. Okay, so as time goes on and the rocket ascends, it uses up fuel, the mass gets less, so the weight gets less. Now if we look at our equation, if the weight is going down, so if this change is a downward change, but the thrust is remaining constant, then the unbalanced force is basically going to get bigger. So we've got an increasing unbalanced force, and therefore we're going to get an increasing acceleration. So unbalanced force increases, and so acceleration of rocket increases. Now that will only last so long as the fuel lasts, of course, but nonetheless it is the case. Okay. There is a second reason the acceleration would increase, so it has some new reasoning here. This time, as the rocket ascends, that means basically that it's getting higher up, and as it gets higher up, g, the gravitational field strength, decreases. Gravity follows an inverse square law, so the gravitational force decreases with altitude. So that means that W as mg decreases. You can see actually that the mass is going down due to the fuel consumption, but g is also going down. So the overall effect, of course, is that the weight's going down. These little arrows, incidentally, don't count for reasoning. They're rough work, so they would be ignored by a marker. You've got to write the words decrease. So that has the net effect of increasing the unbalanced force up the way. As you can see, if the weight decreases, the thrust remains the same. The unbalanced force is clearly bigger. And so acceleration of the rocket increases. And it's obvious that it's going upwards. Those are the two, let me just number them, the two features of rocket motion when it's ascending from the ground that naturally cause the acceleration to increase. Don't make any reference to friction decreasing due to the density of the air going down. That is true, but it's counteracted by the fact that the increased speed of the rocket causes a huge increase in air friction. So you've got two competing effects on the air friction and the high speed winds. So don't mention anything in this regard with rockets due to air friction. It doesn't cause an increase in acceleration at all. So that's rockets, that's part A. Friction, not really much to say about friction, it's really just a reminder of how it works. Well, let's just consider a car. Quite a good car, that one. So if you've got a car moving with a certain velocity to the right, it's going to have an engine force on it, and it's moving through the air. Well, basically the car has to push its own volume of air out of the way to get into the new space. So if the car wants to move 1 meter ahead, it has to push a lot of air out of the way to get into that space 1 meter ahead. And that pushing of the air out of the way requires quite a bit of force. So the car has to actually exert a force on the air. And the air reacts by pushing back on the car and opposing its motion. And of course, that's what we call air friction or drag. I'm just going to call it friction here. It's mainly air friction, but there's also friction in the wheels turning, because any moving part encounters friction. Now, you don't need to know this graph, but I always mention it because it's quite useful to know. And it turns out that with regard to the drag, that's the air friction, air friction is the major component of the friction. The rest of it comes from all the moving parts, okay? But if you plot a graph of velocity in meters per second against drag, that's the air friction, and that would ultimately be in newtons, then what you find is that it rises very rapidly. In fact, the drag is directly proportional to the velocity squared. So if I could just make up some units for brevity, if I've got 1 unit of velocity, say 1 meter per second, and let's just say I've got 2 units of drag there, then if I double my speed to 2 meters per second, the way this curve goes, it's like a y equals x squared curve, I've got 4 units of drag. If I go to 3 meters per second, so I've tripled my speed, but my drag has gone up to 9 units. So doubling the speed quadruples the drag, tripling the speed makes the drag go up by a factor of 9. So drag goes up very rapidly with speed. And eventually the drag gets so big that the frictional force, which always opposes the motion, balances the applied force. So let's remember then, friction is a force which always opposes the motion of a body. The greater the velocity, the greater the air friction or drag. Okay, so again, technically you don't need to know this equation, but it's not an equation, it's a relationship. This relationship, but it's pretty useful to have as an arrow in your quiver, so to speak. Right, So that's friction. The last thing in this note is C terminal velocity. Again, studied at National 5, but we're just flagging up here that you need to know about it. So, probably the best way of dealing with this one is to imagine a body free falling. So, body in free fall. So dropped from a very high building, falling through the air to the ground. So I would use the full width of your page for this. So there's going to be the ground. I'm going to draw 3 diagrams across the page, so one on the left, one in the middle, one on the right, so just keep plenty of space available. And this body is going to be dropped from a fairly substantial height, maybe something like that. Okay. So the body is released, let's say here. And make it down a wee bit actually. Yep, there. There it is. And when it's first released, obviously it's got its weight force pulling it down. So the weight force mg, of course, is always there. But because it's just been released, it's not really built up much speed yet. So very low speed means very low drag. So say it's got a very low speed sort of in there. It's got very low drag in there.